Okay, hi everyone. This video is to go over page 5 of Midterm 2 for Chem 3A, Chemical Structures and Reactivity at UC Berkeley, taught by MaryAnn in fall 2019. Okay, so we are on problem 4A now. This is the first problem on the 5th page, and we are asked to predict the substitution products of each reaction. So let's look at what we've got here, right? This is going to be, this bromine right here is going to be the leaving group. We can tell because the bromine is going to end up there at the end, and because it's a substitution reaction, so that's the only good leaving group. We need a leaving group, we need a nucleophile, we need an electrophile. And we are in a protic solvent, water, right? And we have this silver right here, this silver ion that really, really likes the bromine. Well, I guess the bromine would attack the silver. Anyways, so we've got all of the good makes for a SN1 reaction instead of an SN2. Most of the other reactions in this midterm were SN2, but this looks like it could reasonably be an SN1. The carbocation intermediate in this case would be a secondary carbon, which isn't too bad. Not as good as a tertiary, but it's still pretty good. So, yeah, we're going to assume that it's going to be SN2, or sorry, SN1, where the bromine is going to leave first, and it's going to be attracted to this silver right here. It's not going to be a covalent bond, it's just going to be ionic. So that accounts for the silver bromide at the end. We have the NO3 here that comes from the silver nitrate, and we've got the water solvent, but the water is also going to be our nucleophile. So after this bromine leaves, we're going to be left with this, that, and technically an implied hydrogen here, but this is a carbocation. And the water is going to attack this carbocation and then be deprotonated by another water, which is why we end up with H3O+. So basically, we don't need to show the mechanism, but this is kind of the mechanism that happens. The leaving group leaves, the nucleophile attacks, and so we can have it attack from above or below since this is trigonal planar. And then at the end, another water molecule will take one of these hydrogens. So this isn't happening in the same step, but we don't need to show the mechanism, so I'm just going to show you kind of what's happening. Otherwise, we'd have a plus on the oxygen. That's not really what's going to end up happening at the end. So what will those products look like? They will have this here, this. We're still going to have a wedged line right here. And then we can either have OH wedged or dashed. This is still going to be wedged either way. So there we go. Those are the two products for that reaction. And yeah, so that accounts for everything. We've got the silver bromide, we've got the OH3 that comes from taking one of the water molecules in the solvent and deprotonating the extra hydrogen on these oxygens. We don't want those at the end, so we deprotonate those and we get left with H3O+ at the end, the nitrate from the silver nitrate, and we have our OH that replaced the leaving group. Okay, so now we're looking at the next reaction. It's very, very similar, except instead of this isopropyl right here, we've got two methyl groups. Okay, so it's the same kind of thing. We have a protic solvent, we have the silver nitrate that the bromine is attracted to. So we are going to have the carbocation intermediate. So this is going to be our intermediate step. I guess that's going to be like this plus, and then the water is going to attack the same way. What's the difference here though is this carbocation is tertiary instead of secondary, right? This one had 2 carbon groups attached to it. It had the isopropyl group and it had this other, I guess that's is that sec-butyl? I don't know. It's it's 4 carbons attached to it. But anyways, so it had 2 different hydrocarbon groups versus this one has 3 for the carbocation. So that already tells us it's going to be faster than reaction X because everything else is going to be pretty much the same. The leaving group is the same. The nucleophile is the same. The only thing that's different is the electrophile is the electrophile, the carbocation, is going to be a better electrophile. It's going to, or a more stable electrophile, so the leaving group can leave more easily. The bromine is able to leave quicker because that's the slow step, and the bromine can leave quicker because it's a tertiary carbocation that results. So it's more able to leave. Okay, so anyways, in the end, we are going to be left with oh, and note that the stereochemistry here is actually irrelevant. This is not a stereocenter, that carbon right there, because there's 2 methyl groups attached. So that's going to be the same thing at the end. And because the directions specifically said, do not draw repeat structures, we can only show 1 because there's not going to be a stereocenter there. There's just going to be an OH there and 2 methyls. If we drew like one of them wedged and one of them dashed and then we did the opposite, that would be wrong because that's not a stereocenter, and so we'd be copying the same material twice. So that's why don't do that. Pay attention to the directions and pay attention to where it is okay to draw it like that. You could do that even here, but you can't repeat it. You can't do the wedged and the dashed one and then switch them. That would just be wrong because you're showing the same material twice, since that's not a stereocenter. Okay, last one, and we're given a hint for this one that there are going to be 4 product structures, so we need to pay a little bit more attention. The bromine is still the same leaving group. We've got the same protic solvent and the silver that attracts the bromine, and so that doesn't tell us. It's the same thing as reaction X at the beginning when the leaving group is leaving. But what are we left with when the leaving group leaves? So we've got this double bond here. Got that. Isopropyl, we don't need to show stereochemistry anymore. Remember, we do have this hydrogen implied here. We don't really need to draw, but we can include that. And we have a carbocation. So the thing here is, even though this is the most stable resonance because the carbocation is on a secondary carbon, there's also resonance where this double bond moves here. It's not a super happy resonance because then we're left with a carbocation on a first degree carbon, primary carbocation. But it's still valid resonance. There's those 3 conjugated pi or p orbitals. And so that makes this intermediate more stable than X, or is that what it's called? More stable, yeah, than intermediate in X. Even though this is the most common resonance structure, this one is still a valid resonance structure, so we need to consider it. And that makes the bromine able to leave quicker, which is the slow step for these reactions anyway. The leaving group leaving in an SN1 reaction is the slow step. And so because the bromine is able to leave quicker than in reaction X, that means that this problem is going to be faster than reaction X, because the bromine is able to leave more quickly because of the stability, because of resonance. Okay, so it's going to be the same kind of thing for the first two products, where we can have our two resonance structures. We can have the isopropyl like this, and the OH here, or the isopropyl can be pushed back in the OH here. Again, you could also instead draw, that might be easier so that we're more like reaction X, where we draw a wedge to the OH and draw a dash to the OH. These are still valid though, they're the same thing. Okay, so those are two of the product structures. But like we said, there's resonance going on right here where there's a carbocation right here. And so instead of the water attacking, let's do a different color. Instead of the water attacking right here after the bromine leaves, we can instead have the arrow pushed and then the OH2 attacking here at the same time. So that leaves us with let's see, so the double bond is here. We've got the isopropyl and the OH that's no longer going to have stereochem, the wedge or dash. And we've got the OH, oh no, not, that's still a carbon. We got to watch out there, don't miss out on your carbons. And then an OH attached to the carbon. And then we've got the other isopropyl group down here. Okay, so that's one of them. And then the other one is if we rotated this starting material from the beginning so that we have, here let's do a different color. Rotated this from the beginning so that we have a double bond isopropyl, and then this isopropyl and the bromine. Remember, you have to rotate this sigma bond before having the bromine leave, because you can't rotate this bond here after the bromine leaves. If you did have to show out these steps, you can't do that because of the resonance here. The conjugated p orbitals prevent rotation of a sigma bond if a double bond is possible in that location. So you actually have to rotate it up here and then have the bromine leave, and then in a separate step have the double bond move at the same time as the water attacks. Okay, so first step, if we had to draw out this mechanism, I would not do this all in one step, but this is first step, and these two are second step. And then of course the other water deprotonating one of these waters would be the third step. And so we'd end up with something just like this one, except with the isopropyl groups cis to each other. So we'd have the carbon OH, isopropyl, and OH. Okay, so those are the four product structures. Let's double check the key and make sure I did that. Yeah. Oh, we're not supposed to have the OH on the end. That's my bad. I was counting the OH that's added over here as part of it. That's not true. Instead of the OH being added there, we're adding the OH on the other side. So those are just hydrogens that are there. That was my bad. Pay attention to the question. Oh, sorry, that's really confusing. Yeah, instead of the OH2 attacking here, we just have the hydrogen there, and then the OH2 attacks over here. So that's why it's just a hydrogen here. Hydrogen there. You don't need to draw those in though. Okie dokie. Last question on this page says draw a curved arrow mechanism for the following reaction. And so we have hydrobromic acid as our catalyst. That lets us know that we are going to use it to make the reaction go faster, and we're going to get it back at the end. And so this is a strong acid, and we know that we're going to want this group to leave at some point because we end up with water at the end, and because the methyl hydroxide is probably this O methyl group right here, this alkoxide, and so or it leads to that. So actually let's put that in a different color so that we can see that's what we're talking about. Methyl hydroxide is probably going to lead to this methoxy group that's on both of these. So let's have an acid-base step first that will make the leaving group a better leaving group, right? Because OH is an okay leaving group sometimes maybe, but it's better if it's a water. So let's draw out this catalyst HBr, and the bond will break between the hydrogen and the bromine, and the oxygen will snatch up that hydrogen. So acid base to make better leaving group. You'll recall this is a pretty favorable acid base because hydrobromic acid is a really strong acid. It really wants to get rid of its hydrogen, and water isn't as strong of an acid, so it's overall going to be favorable. So we have OH2 here, and we have our methyl group here, and now we have a plus charge on that oxygen. We have bromine with a negative charge, and so now this is a really good leaving group because water is happy on its own. So yeah, let's draw our next step. So now we're left with the carbocation, which is pretty stable. It's a secondary carbocation. We have this methyl group here, and we know that it's going to be a carbocation intermediate instead of an SN2 because we are left with two products at the end. So that kind of gave us a hint too. So now we're going to have our methanol attack. So let's just draw that as MEOH. And so this can attack from above. Let's draw two different colored arrows. So we can have it attack from above, or here, draw that. We can have it attack from below. You'll recall this is trigonal planar. Yeah. So then we've got oxygen. This is a carbon. Still got this methyl group. And then if we're above, we're going to have oxygen, an H, and a methyl. This is going to be a plus. And then we'll also have oxygen. So they're 5-membered ring. Now the methoxy or the methanol attacked from below. And still has a plus charge. And this methyl will still be wedged. And then lastly, we have the bromine ion And the HBr was supposed to be a catalyst, which means that we're supposed to get it back at the end. So we're going to have that bromine deprotonate that hydrogen. And we're going to have another bromine deprotonate this hydrogen. And the electrons go to the oxygen, and that's what leads us to this one and this one. And we got the water right here, H2O, because that came from that leaving group. Okay, so that is page 5 of midterm 2 for Chem 3A. Thank you for watching.